In this lecture, we're going to talk about multiple regression. This is going to be the last of the regression topics we're going to discuss. Our objective is pretty much like the case with the simple linear regression, the first order model, where we had a single independent variable x. The difference is now that we have multiple independent variables. We could have 2, 3, 4, or as many as necessary. So here I have the objective. We want to still do the same thing we did before. We want to predict the value of response variable. And I want to emphasize what we are predicting in all your regression analysis is the average, the mean, or the expected value of the random variable for a given value of x. So the analysis is going to be very similar to simple regression model. The deterministic multiple regression model looks like this. What we mean by deterministic is that there is no error involved in this. Okay. Now we do have a probabilistic actually model that we use, and all we do with the probabilistic model is to add an error term at the end right in here. Okay, so that's going to be the only difference between what's deterministic and what's probabilistic model. Okay, so the probabilistic model allows for the error, and that's what we're going to be using. So what are the betas here? Notice the first two terms here, these two terms, are exactly what the case with simple linear regression is. And that's how we chose to go with b sub 0, b sub 1 rather than mx plus b, the usual algebra notation for the line. So we can see the utility of that notation in a multiple regression model. So the betas here, other than beta 0, betas, beta 1, beta 2, beta 3, and beta sub k, assuming we have k independent variables. These are the coefficients, and more specifically, these are the partial coefficients for each of the independent variables. Okay, now beta 0 would be like the y-intercept. And of course, we don't have a line here. The case where we have two independent variables, actually the response surface is going to be a flat surface. So the line turns into a surface in 3 dimensions. But beyond that, we really don't have a geometric interpretation of that. So here is a description of all of these betas. And again, I want to emphasize the partial regression coefficients. And why is it called partial? Because I have it right here. Partial is because we have more than one predictors, and that is the reason it's called partial. So here again, I have 3 notes. Note number 1. In a multiple regression model, the interpretation of beta sub 0, and of course these are assuming population models, by the way, because we're using betas. Usually when you use Greek letters, that means we're using population parameters. But of course we have a sample version of this where the betas turn into lowercase b's. So this will be b0, b1, b2, b3, and so on. And the second note I have here is that the interpretation of partial. What do we mean by the word partial? So the partial regression coefficients here, the interpretation of it is that it indicates the coefficient here on an independent variable, the beta, indicates the increase, or it could be decrease, because if it's negative, it's actually a decrease. But in general, it shows the increase in the value of response variable for 1 unit increase in that independent variable. So maybe I best change that to represent the increase. Let me go / decrease actually in this one, because again, it could be positive or negative. If it's positive, the coefficient is increase. If it's negative, it's a decrease. But here's what's important. Partial means all other variables are held constant. That's what that is, assuming all else being equal. Okay, so what do we look for in a multiple regression output? These are the things that we typically look for in an output. We're going to look at the regression equation. That would be the regression model. the fit for the response variable. We definitely look at the coefficient of determination, r squared. We do not look at r anymore, right? Remember r, the Pearson correlation coefficient, that's only for simple first order models. We look at adjusted coefficient of determination, so that's r squared adjusted. We look at the p-value in the ANOVA, and that p-value in the ANOVA tests the overall global hypothesis that we have the right or we do not have the right model, the overall fit of the model. And we look at for individual now p-values to test the significance of each of those individual regression coefficients. I'll tell you more about it from the output and why we do that. And of course we look at S, which is the standard error of the estimates. This would be the standard error, the standard deviation about, let's say, the regression. Okay, it's called the regression, standard error of the regression. So let's take a look at this example. Okay, so in this example, we're going to use the following. Use the following data to predict the amount of prepaid card purchased at Starbucks using customer's age, the number of days per month the customer makes a purchase at Starbucks, the number of cups of coffee the customer drinks per day, and finally the customer's income. So in this case, we're going to have 4 independent variables, 4 regressors or 4 predictors. What we would like to predict is the amount of prepaid card they're going to purchase. So that amount, let me just call that response. That's what that is. The rest of them, these remaining variables, are going to be independent variables. Okay, and here's the actual data for this that you're looking at. So here's customer 1, 2, 3, 4 all the way up to customer number 25. And then this is how much they bought the prepaid cards from Starbucks. This particular person was 25 years of age and went to Starbucks 4 days a month. And this person, he or she drinks 1 cup of coffee a day. The person's income is about $20,000 per year. This person purchased a $50 prepaid card from Starbucks. This person too was 25 years. Look at that, 25. So we have repeated measurement. And this person spent 12 days in a month in Starbucks, and he or she drinks 5 cups a day. So notice higher purchase of prepaid cards. And this person's income is $60,000 there. So on and so forth. I've highlighted this one particular person. There's only one person in the sample of size 25, okay, that purchased the prepaid card of $200. And that person's income, look at that, $80,000 a year. So I guess that's interesting to note. This person's age was 40, and he or she visits Starbucks 15 times in a month and drinks 5 cups of coffee a day. So really an avid coffee drinker. Okay, so now I'm wondering if age has to do anything with the amount of purchase, of prepaid card purchase. So you may argue it really has nothing to do with age. How much you're going to pay for is what you can afford, right? And what you can afford for most parts depends on your income. Okay, so let's continue on. And this information I actually imported from Excel. So I typed it in Excel and then imported it into my note. And I've also imported it into Minitab. Okay, I copy and pasted it into Minitab. So here's the regression output. So most of these are familiar with us because we've come out of chapter 7 when we talked about regression. So this is the regression analysis of prepaid amount versus age, days, cups, and income. So this is the actual regression equation. Negative 83.8 plus 0.237 times age plus so on and so forth. Notice that the coefficient on every one of the variable is positive. So 1 unit increase in every one of these will increase the purchase price, the expected purchase price of prepaid Starbucks cards. Now, these are the coefficients, of course, on the parameters. All of these numbers that you see here, these numbers are up here. They're just in the column format. So this is the coefficient on age, on days, cups, and income. The standard error of the coefficient, this is actually like the give or take of each of these variables. Okay. So in other words, we estimate the coefficient on age is 0.237, give or take 0.576. Days, 1.19 is the coefficient, give or take that. Now, here are the p-values. So what are these p-values testing? Usually we do not test hypothesis about the constant. Okay? Because if you don't need a constant, we just don't put it in the model. But a lot of times we want to keep that constant. So we don't usually check this. We're going to ignore this. But if you should know what this means, anytime, remember, you see a p-value, that means somebody's testing a hypothesis, right? Or a hypothesis is being tested. So 0.001 rejects whatever the null is. In every one of these, the null says, in this case, the null says I don't need constant. The null here says you don't need age in the model. You don't need days in the model. You don't need cups. You don't need income. Now those symbolically means beta 1 is 0, beta 2 0, beta 3 0, beta 4 0 individually. Okay, that's what it means that we don't need age. If that is 0, you don't need that variable. And of course, a t-test is being done. Now the p-values, check out these p-values. Remember, p-value small, we reject the null. Large, we do not reject the null. So the only significant p-value is actually this one, right? So that p-value is highly significant. It's almost at 0, right? So that means we're going to reject that null hypothesis. Okay, I'm talking about this one right in here. So we definitely need income in our model. Okay, so the hypothesis this one is testing is that beta 4 is equal to 0. And we're going to reject it. And the rest of them, though, look, we're not going to reject the rest of them, are we? And check out this other one in here, for example. This p-value is testing the hypothesis that beta, that's days, right? Beta 1, 2, that's beta 2 is equal to 0. We do not reject that hypothesis. That means the coefficient on x2 is 0. So that what that means in effect is that you don't need days. In presence of income, cups, and age, you don't need days as a predictor of the amount of prepaid cards that will be purchased at the Starbucks by the consumers or the customers. So that's what these individual p-values do. They're very important in our work, by the way, everyone. Because a lot of times what happens is, in order to select a good predictive model in regression, people just put a bunch of independent variables, 7, 8, 15, and so on. And it turns out that a lot of those variables really do not contribute anything to the prediction. They don't improve the prediction that significantly. So that's where these p-values come in very handy. Of course, remember, we don't take care about this one because it has to do with the constant or the y-intercept. So these other p-values are very important in our work. Okay. Now, the other thing that's in here, I'll explain this in greater detail down below. The VIF here, I just want to mention this because it's there. Otherwise, I wouldn't. This VIF is an acronym for Variance Inflation Factor. Okay, so Variance Inflation Factor. What this variance or VIF inflation factor does is actually looking at whether there is multicollinearity between these variables. What do we mean? I have all of these coming up, so let me save that for later. But that's what that is. Now, here the model summary. So I'm looking at actually this segment now. In our model summary, R squared, we know what that is, right? Coefficient of determination. Remember, R squared must be 70% or higher to have an adequate predictive model. So the R squared here is about 75%. So what that means is 75% of the reason for why people purchase different amount of Starbucks, let's say, prepaid cards, 75% of the reason has to do with their age, how many times they go to Starbucks, how many cups of coffee they drink a day, and what is their income. The other almost 25%, we don't know. There are still 25% other reasons why people purchase different amount of prepaid cards. So the question might be, well, how come not everybody purchases $25 prepaid card or $50? Well, the reason why not everyone that purchases prepaid cards from Starbucks, 50, 20, whatever amount you're thinking, is because of their age. Those are the factors that are influencing the amount of prepaid cards that are being purchased. Okay. Now, the other thing that we need here is important is this one, adjusted R squared. Now remember, in the case of simple first order model, we don't care about adjusted R squared because you only have one independent variable. But in multiple regression, what we like to see is that these two numbers should be close. So this is actually, see how far off they are. So what this adjusted R squared does, it actually keeps track of how many independent variables are in the model. And it actually, as you add more independent variables in your regression model, you get penalized for it through R squared adjusted, the way the formula was designed. So it actually penalizes you, and that's why R squared adjusted drops. Notice it's marginal here, right? 70%. So this is still okay, not too far from 75. So that's why in a multiple regression model, we actually pay more attention to this than we do to R squared. Okay, but in this case, they're both good. So this is an okay model for prediction, an okay model. This S here is the standard error of a regression model, the regression. Okay, and that would be the error of prediction at for every levels of independent variables. So for a given age, given days, given cups, given income. When we make a prediction, and we'll see that's coming up. When I make a prediction, whatever that prediction of the prepaid amount that's going to be purchased is going to be off by about $22. This is in dollar figures, right? Because that's what your prepaid value is. The amount is in dollars. So any purchase prediction we make, it's going to be off by as much as, it could be off, I should say, by as much as $22. That's a lot when you buy a $25 gift card, right? But again, why is that so high? Well, because your R squared isn't that impressive. If that R squared was large, like 90%, I bet you that S would be much smaller. So that means more accurate predictions. And this is what the ANOVA looks like. Remember the analysis of variance. So here's how Minitab puts it. Remember, for simple linear regression, first order model, chapter 7, we only had the regression, we had error and total, right? We only have those. Now, because we have 1, 2, 3, 4 independent variables, so Minitab actually shows the contribution to the overall sum of squares due to individual sum of squares. Now, the greater the sum of square, by the way, in regression, the better. That means we're picking up more and more of this number of the total variations. Okay, now these 4 variables combined are picking up over 30,000 of the almost 40,000 number for the total variation. Between these 4 variables, if you look at this one, let me clear this up so it's not too cluttered. Okay, so now I'm just looking at income. Look at income and look at this number. See that? So of this 30,000 and change total sum of square due to regression model, almost 22,000 of it comes from income. So that means income is playing a big role in explaining for the variations in total. Okay, so this is total variation, by the way, in Y's. Okay, that's in Y values, in Y's. That's in prepaid cards. The total variation in prepaid amounts is due to these 4 sources of variation. What's causing the variations? So anyhow, and then you have a set of p-values here. Okay, so in the analysis of variance table, if you look at these p-values, 1, 2, 3, these 4, let me go up, 685,429, and I don't have to go too far up. There you go. You see these? 685,429, 595. They're exactly the same. Now, this number, the triple zeros here, this has to do with the overall regression model. Okay, so what that number is doing, that p-value, is testing the hypothesis that we have the right regression model. Again, that's just this one. We call that the global hypothesis test in the ANOVA. Okay, so that's just saying, do I have the right model here or not? The answer is yes. So you got the right model. It's just, you can make predictions with it according to the R-squared, right? It's just not a very powerful model, but it's okay for making adequate predictions. So again, that's the significance of the first p-value that goes with regression, this one. So again, this p-value is testing the null hypothesis that the model is the right predictive model. Okay. And of course, Minitab just puts this out. It says you have an unusual observation here. Remember the one I had highlighted in my data points? One person purchased $200 prepaid card. Ordinarily, people don't do that, right? So there you have it. That's why, in fact, it was flagged. So usually they're flagged, and who knows, maybe that was a $20, right? And someone put that in error. Who knows? Or it may be legitimate. But the point being, the Minitab kind of flags it for us to make sure that it's legit. And the fitted regression line says the fit here, it expects this number to be 143. That's the fit based on the regression model. Okay, the predicted value. And how was this number 143, by the way, predicted, if you want to know that? Well, here's what happened. Let's look at the 200. That's right in here. Okay. So if you put 40 for age, 15 for how many days a month they visit the Starbucks, and 5 for how many cups of coffee they drink, and 80 for the income of the person of that income, and into our regression model, right, that was put out into this model right in here. If you put those 4 numbers in here, this ends up being in the 140 and change that we just saw. Okay, so that's where they're coming from. That's where this number came from. All right. Now, this is the residual. Remember, the residual is the difference between them. So that would be 200 minus 143 equals the residual, or the error, or the miss, or the leftover. And this is just a standardized residual. Okay, just so you know. All right. A lot of times we use the standardized values to compare the coefficients. So in fact, we even can look at the standardized coefficients. But this idea of regression, everyone, especially multiple regression, this is big. This is actually very huge. So in fact, you could spend the whole year trying to go through a regression textbook and learn and know all that you want to learn about the regression. So it's very vast, very deep, very involved subject. So we're just doing some illustration of the use of it. Now, we're getting into that VIF, the variance inflation factor. Okay, so in every multiple regression analysis, everyone has to pay attention to what we call multicollinearity. The multicollinearity, that's when variables kind of overlap. You have redundancies in your independent variables. So 2 variables are measuring pretty much the same thing, the same attribute. So when we talk about collinearity here, we refer to predictors that are correlated with other predictors, with one another. So multicollinearity, when does this happen? Okay. Well, this happens when, again, you have duplicate efforts in some variables. So for example, if you look at, I don't know, your arm circumference and your forearm circumference, let's say there may be some kind of correlation between them. Okay, so and the correlation between them mean the bigger the arm, the bigger the forearm. So if I'm trying to measure, let's say, the body mass index based on those 2 variables, well, one of them is enough. I don't need both of those variables. So we have multiple factors that are correlated, not just your response, but also to each other. Okay. So the factors become redundant here. And one way to actually measure multicollinearity is a VIF, the variance inflation factor. Okay. Now this variance inflation factor, again, tells us how much of the variance of the regression coefficients increase if your predictors are correlated. And to find it, because notice up here we had like 4 or 5, well, we had right up here we have 4 different variance inflation factors, right up here we got 4 of them. And if you want to know like how does Minitab calculate it, is actually it does a regression. It regresses age against the other 3 to get this number. Regress days against age, cups, income, you get that number. And so that's kind of the basis of how it's done. Okay, just to point that out. Now let's go further south. And as a rule of thumb here, by the way, means what works. As a rule of thumb, we actually look for variance inflation factors that are less than 10. 1 is perfect. So less than 10 is ideal. If VIF is greater than 10, that means you have high multicollinearity. So again, here's a regression equation that you're looking at in here. Okay, and let's say I want to predict the average amount of prepaid card that will purchase by an individual who's 35 years of age, visits a Starbucks 12 times in a month, and this person, he or she, drinks 3 cups of coffee per day and has an annual income of $50,000. So there you go. And what I've done here is I actually put these numbers, like 35 years of age, you put 35 up here. And there you go, I put in the regression model. So all of these numbers, 12 goes in here, and 3 cups a day goes here, and $50,000 means 50. Remember, these are coded values for income. Each number is in thousands for income column. So I rounded it to $64. You would expect a person with these attributes to purchase a card for $64. Now, of course, I know that in Starbucks, unless you can charge a card and say, give me a card for $64, they actually have denominations that range from $5 to $500 in $5 increments, I believe, but whatever that might be. This is just a theoretical estimate. Now, to the right of this, by the way, there is a way to get Minitab to make that prediction for you. And you can see it in here. So, right in here, see these numbers? These are the ones that I have up here. So, I input those, and I'll show you how to do this in Minitab in a few minutes. So, you just give it the values of those variables, and one by one, it gets plugged into this, this, and into this. Exactly what I did on my calculator, but it gives you actually more. So here's the fit. The fit is the predicted value. It's that $64. I rounded it. The standard error of the fit, think of this as like, we need this in order to construct a confidence interval. Okay. Now this is interesting for the confidence interval. I use the default 95% confidence interval. So we expect a person of those with those attributes to purchase a prepaid amount of $64, and that person could purchase, on average, the average person with those characteristics, the average person purchases anywhere between a card that's between $40, almost $7 to $80. That's what we expect to see. That's your confidence interval. Again, on the average person with those characteristics will purchase that amount that lies inside of that confidence interval. Now, next to that, we have PI. Notice this is CI, right? Confidence interval. PI stands for prediction interval. Now, the prediction interval takes the word the average person. So let's say a person now, not the average person. I'm going to go in there, or someone is going to go in there. That one person who's about to enter Starbucks. He or she is not your average person. It's just a person. And that person is 35 years old. That person that's about to enter Starbucks goes to that location or any Starbucks 12 times in a month. And that person drinks 3 cups of coffee a day, and that person, see, one individual, that's what this prediction is. The prediction interval predicts how much one individual is going to spend, not the average individual with those attributes. Anywhere from $14 to $112. Notice much wider range and not as wide. This one, again, it looks at the average person, looks at mean. This one looks at an individual. Okay, so that's the difference between them. But nonetheless, that's Minitab gives you that. Now, how accurate is this estimate of $64? Well, this estimate could be off by as much as $22.14. And that's what the S does. Remember, we did that in our, in our simple regression model. So any prediction you make could be off by as much as $22. $22. So anywhere here on average, anywhere from subtract 22 from that, you get $42 all the way up to $86 for this particular one. Okay, that's what the standard error is. Okay, there is no confidence level, there is nothing involved here like I have here, confidence level 95%. That's a different thing. Okay, now again here I'm just going over the things that we look for in a regression output. So I'm going to go through these bullets now, make sure I covered all of these things that we typically look for. We will look at the regression model, which of course I've used it, I showed it to you. We looked at the coefficient of determination, of course, yes, r squared, that's the coefficient of determination, and there it is right in here, r squared. Adjusted coefficient of determination, we talked about that one. The p-value of the ANOVA, we actually did that when I talked about the ANOVA, but here I have it down here again, you see that? Analysis of variance, regression. Don't worry about individual parameters. So, and that's what that is. This p-value again tests the overall fit of the model. The null says you have the wrong model, your model is inadequate. Alternative says no, it's a good working model, and in this case we're going to reject the null. We're going to say no, this model is an okay model, can be used for predictions. And we look at, of course, the individual p-values, which I did that, and we look at the standard error of the estimate S, and that standard error is right in here. Okay, so there we have that. So I've gone over all of the bullets. Okay, and of course I put this global hypothesis for you. The null says model is incorrect, and this set of hypotheses right in here, that's what this p-value is testing. So we're going to reject this null. Model is incorrect. We're going to reject it. So we're going to side with the alternative. That means no, we have the right model here. No problem. Okay. Now, the next question I have down here. Do we really need all of these predictors in the models? Remember, having these predictors is costing us on the adjusted, right? The adjusted r squared right in here, we're getting penalized about 7% because we have too many variables perhaps. So that's what we want to answer. We're going to look into this. Let's see how we're going to answer this next question. Now, to answer this question, we're going to take a look at the individual p-values that we looked at right in here. And we already answered this question, right? So it turns out that we do not need these three variables. We're actually getting penalized. It's costing us 5% of that r squared, right? You're roughly about 5%. We'll see that. It's not automatically. You subtract that and you get 70% from what I had up there. I'm just guesstimating. So there you go. Whatever it's costing us, but these three are actually costing us precious r squared. And also, by the way, look at the variance inflation factors. All of these are about 1 to 2. So there is no multicollinearity here between the variables. That's good. So according to what we see, though, individual p-values, it looks like we do not need age, we don't need days, and we don't need cups. We can do away with them. So that's what I have here. It looks like income is the most significant by itself predictor of how much a person is going to buy when they get to Starbucks, those prepaid cards. Now, what I did is I said, okay, so it's like, okay, then what do? Do I throw them away? Yes, you actually do. So I actually created a new simple model, regression model, and there you go. This p-value in the ANOVA, again, is almost 0, means yeah, the simple linear regression actually works well here too. And if you look at now, see your adjusted R squared, or adjusted R squared up here, right up here, was 50.56, right? Oh, I'm sorry, 70.56, and R squared 75.5. So look at our R squared slightly dropped. So having those 3 variables was only boosting R squared by 3 percentage points. That's not much. And a lot of times it's like maybe you don't want to track these variables, they're hard to get, so for whatever reason you're just looking to dump them, and this will help us do that. Okay. And I made a new prediction based on this regression equation, and based on which regression I'm talking, this one. Okay, so I made a new prediction. I plugged in 50 in here, multiplied by 2.579, subtracted 63.3, and I got 64 down here for all of that. Right in here, see, 64. Now note this prediction is not too far from the previous one. Remember, previous one was about $64, now about $65. And then the other thing I did, I said, okay, well, let me now put those 3 that we just threw away. I took the most significant independent variable or predictor income, the one that the regression model said you needed. I actually took that out and I used a 3 variable model. The not so good predictors are all in there together. Now, look at the p-values. When you take income out, this model actually is going to be a very poor model for prediction. Okay, and that is actually found through the new R squared. Okay, so if I look at now the R squared for these other variables, look at that R squared. Look at the adjusted R squared. My goodness, check this out. See the discrepancy there? So this is definitely a poor model. Okay, poor model. And the R squared for predictions, that means how they come up with this is that they use the regression model and made prediction for all of those actual observed values with those x1, x2, x3 values. They actually substituted with those numbers and they got entirely a new whole set of predicted values. And the R squared for prediction, 0. Means really lousy. Means this is the worst they can get. But we knew that, right? These p-values are telling us the same thing, that every one of those coefficients are 0. So those are not effective in making predictions. Okay? And if you look at the ANOVA, remember the first line of the ANOVA is the global hypothesis here. That says you have the right predictive model. The null says you don't. And we do not reject the null now. 0.176. So we do not reject the null. Null prevails. This is not a good predictive model. And now, the next thing we want to do, so hopefully that clarified how we determine which variables in the regression model we're going to keep, which ones we're going to discard or throw away. Now, let's interpret the coefficients. Now, this is important for the regression output and in context of every application. So what I have is actually these coefficients. Remember, these are the estimate of the betas. So this would be B1, B2, and this is B3, because these are sample coefficients, right? The populations are betas, samples become B's. So here's the interpretation of this number. Remember, that's the coefficient on age. So the amount of card purchased on average increases because this is positive. In fact, these are all positive, so every one of them will be increased. So the purchase amount increases by 23.7 cents because that's $0.237. 23.7 cents for each additional year increase in age. So a 30-year-old person goes in, whatever they buy. 35-year-old person goes in, 5 times 24 cents. That means they're more likely to spend 5 times 25 cents, $1.25 more, just due to their age. That's assuming all other variables are held constant. So that means, again, if I just look at the coefficient on age, that means the other 3 variables, all of these are held constant. We only allow this to change. So 1 unit increase in age has an effect of increase in the amount of prepaid by this amount. Okay, that's holding everything else constant. And then we move on to the next one. Notice there's 4 variables here, so we have 4 coefficients to interpret. I've interpreted 2 of them. You can interpret the other 2 that I have not. I have done age, the interpretation of coefficient on age, and I've done interpretation on number of days a customer visits per month. That's this one, right? Number of days. These other 2, you can try to interpret them. So the amount of card purchase, and however you interpret as closely to what I'm saying, what's important, all of us would be talking is this: on average, on average. Next one, you will have those keywords, on average. Because everything we do in regression has to do, all the predictions are about the average response, effect on the average response, the response value. So number of customer visits per month tends to increase if, in other words, let's say I go there 10 times in a month. The next person goes there 12 times a month, 2 days more than I do. So 2 times $1.19. You expect that person, just by the virtue of how many days they visit per month, 2 more days than I do. So you would expect that person to purchase $2 and almost 40 cents more on the prepaid card. Okay. And let's see, that's about it here. So we're done with this. Now let me go to Minitab. So I'm going to pause this video and then bring up Minitab and resize my presentation window, and then I'll be back shortly. Next time when you see me, I'll be in Minitab. Okay, so here I am in Minitab. I got out of my note, now into Minitab. Here is the data that I have already generated. I have input that data. I copy and pasted it from Excel. Actually, I had it in Excel and then I copy pasted it here. So here's the raw data. Okay, I'm showing my viewing window output. Okay, now it's better. So let's say we want to do a multiple regression. You're going to go to Stat, and then you go to Regression, Regression again. So you go Stats, Regression, Regression. And you want to go to Fit a Regression Model. And there you go. Now let me remove this one. So when you go in and you click, you activate in that cell. Let me remove all of these. Okay, so when you first activate the cell, there you go, it should be blank. But once you click in it, you should see the columns with data. These are the variables. Okay, so my response is what I want to predict, right? My predicted value, the variable is prepaid amount on the card. What am I going to use for my predictors? I'm going to use age, double click, days, cups, income. Okay. Now, categorical predictors, I don't have any. These, all four of these variables, predictors, and notice, by the way, how Minitab calls dependent variable response, independent variables predictors. So the assumption is you put all of the continuous ones here. In other words, the quantitative variables go in here, independent. If you have any qualitative, goes here. For example, gender 1, 2, or let's say if whatever that could be qualitative. Okay. Does it have a basement? Yes, no. That all of anything that's categorical or qualitative would go in here. So that's why it is possible to actually do regression with qualitative variables. Okay, so anyway, this is what we have. And in here, don't worry about anything in here. Some of these graphs, like if you click on it, these are our diagnostic graphs for the probabilistic model. Okay. And of course, all of these you can change. Go options. Yeah, you can make transformations. You can do weighted regression if you want to de-emphasize the effect of, let's say, days. You can use weights and so on and so forth. But we're going to just stay with the basic ones. And there you go. Let's click on the model. Now the model here, we're going to keep it at the default that it is right in here. Terms in the model are age, days, cups, income. If you want, you can create interaction models, so on and so forth. Like the interaction of days and cups, age and income, things like that. So just leave everything alone and hit OK. And once you do, you're going to see the output that I had. You see this? So all of these numbers are the ones that I had. I just copied the image of the individual parts of it into my notebook. So there you go. You have all of those. Now you can actually get this to make predictions for you. And here's how you can get it to make a prediction, like the prediction that I made earlier. Remember the one that I did in my example? So here's how you get it to make the prediction. You go stat, regression, and this time, there you go, see? You go predict. It already has a regression model, but if you run this for several variables, then of course it gives you options. Well, which of these models you want me to run these numbers for? So the only one we have. And in here, what am I entering? Columns of the values? No, we're doing individual values. So remember, the person was, let's say, a 35-year-old person goes in who visits a Starbucks 12 times a month and drinks 3 cups of coffee a day, whose income is $50,000. See? This way you don't even have to use your calculator. You let StatCrunch you let Minitab do this. Then you can kind of look at this view model. There you go. That's just to make sure you have the right model. The model uses the current data. Close. The results, regression equation, prediction table. So you can just tweak these and see, click on them, see what happens. Options. Do you want confidence level 95%? Sure. Interval, type of interval, usually we go two-sided. So let's do a 95%. In other words, we're going to do our prediction, confidence interval for our prediction. Okay. And there you go. This is what I had again in my OneNote. So the fit is 63.3. The standard error of the fit, actually this number is used in here in conjunction with constructing these confidence intervals. This is 95% confidence interval for the average person with those characteristics, how much they charge or how much they purchase. And this is 95% PI, prediction interval, for a single individual that's about to walk into Starbucks This person is not the average person. It's just a person. And it is true that always prediction interval is going to be wider than the confidence interval, because it picks up the variability of the means plus the variability of the individual in there. Okay, and there you go. With that, we are done with this video. Hopefully now you know about how to run a multiple regression model in Minitab. And we are done with this video.